Hi and welcome back. This is video 2 of 3 for chapter 12. And in this video, I would like to discuss three big concepts. The first big concept is something called Ampere's Law, which is I'm not going to say simplification, but it is a version of a more general law called Stokes' theorem. Now, we're then going to use Ampere's law to talk about what's called a solenoid, which is the magnetic field equivalent of a capacitor. Now, that said, let's talk about Ampere's law. So, Ampere's law is sort of like Gauss's law in that it allows you to relate the properties of a field to the thing that's creating the field. It's more complicated conceptually because one version of it through Stokes' theorem involves something called a cross product. That is a curl is what we call it. And you'll see that here in a moment. That said, I'd like us to consider a specific situation. So let's imagine you have an infinitely long line of current. It's constant, has a value of I. Now, in the previous video, we talked about what the magnetic field looks like. It looks like this. It curls around. If you remember, mathematically, B is going to look something like, if you were to call this, we'll say the z direction and this the xy plane, mu naught times I theta hat over 2 pi times r being this right here, how far away you are from your wire or your source of constant current. Now, if you were to look at this from a front view, that is right here, you have the current coming out towards you. What you would see would be the magnetic field circulating around it like this. Here, the direction of I is out toward you. If you put your thumb in the direction of I and curl your fingers around, what that does is to tell you that your magnetic field goes around in a circle like that. That's your angular direction, your theta hat direction right there. Okay? Now, so Ampere's law states the following, basically, that if you were to integrate over a closed loop, the magnitude, or not the magnitude, but your magnetic field dotted with dl, you would get mu naught times the current that is within the loop. So let's see if this is true. We're going to prove this. And we're going to prove it for this specific case of, an infinitely long wire carrying current I in the magnetic field that we have here. So along our little circle right here, we'll put our circle right here, has a radius of r. Okay. This is our loop that we're going to integrate over. Along this, the magnetic field points this way. But if you think about Cartesian coordinates, x and y, This is also the direction of positive angle. And if you were to walk in this direction along DL, DL is going to be along the loop that we've drawn. Then DL would equal to R d theta, theta hat. Remember, DL is based off of arc lengths. S is equal to R times theta. R is constant for the loop that we've drawn, and we're just integrating along the angle. Now, so B itself, along this, only depends upon R, and that's it. How far away? So B dot DL would be mu naught I over 2 pi times capital R, since that's the radius of our circle here, theta hat, dotted with R d theta, theta hat. Theta hat's parallel to theta hat, which means the dot product between it is 1. And you have mu naught I R d theta over 2 pi r. Now, if you take a look here, you'll see the r's cancel just like that. We're integrating around a circle. It's closed. Everything here except for d theta is a constant. That is equal to mu naught I over 2 pi. Our closed loop starts at 0 and ends at 2 pi. When I do this integral, I get 2 pi. You'll have a 2 pi on the top, a 2 pi on the bottom, which means at the end of the day that's equal to mu naught times I. So as you can see here, Ampere's law, which is this right here, is true. Much like Gauss's law tells you about the electric field due to the charge trapped inside of the surface, Ampere's law tells you about the magnetic field due to current that's passing through a closed shape. Okay? A closed shape, not a surface, just a shape. Now, this thing is, for magnetic fields, very useful. Okay? But before I get to using it, what I would like to do is to talk about another version of this, which is what you get when you invoke Stokes' theorem. So, this is Ampere's law. Now, Stokes' theorem is a mathematical theorem, much like Gauss's law truly is a mathematical theorem as well. And what it does is to relate closed loop integrals, and I'm just going to use A for sort of a general vector, to the areas via something called a curl. Now, this looks a little bit like the relationship between divergence and charge that we saw with respect to the electric field. except this deals with something called curl. Curl tells you how much a vector field rotates, how much of a curl, how much of a spiraling there is to it. And so if I were to take and plug this right here into the left hand side, what I would get would be something that looks like this. Whoops. Now the surface in this case would be, if I looked at this example, this circle right here. It would be, this is the surface right here. It's not a closed surface, there's no little loop to it, it's just this open surface right here. Or this surface right here, if you're going to think of it like that. So on the right hand side of Ampere's law, we have this mu naught I thing. Now let's talk about what I is. I we know is current, but current is related to something that we've talked about as well in the past, and that's something called current density. Now when we talked about it, we were talking about current specifically with respect to resistance and Ohm's law and what have you. But current density you can think of, and we use the letter J for it if you recall, as how much current passes through an area. Okay? So here, for example, we could talk about the current that passes through this area right here at any given time. Now what that means is that if I look at this and I solve for I, and then I sort of promote this to a differential, and we're going to assume for constant current in this case that J is constant as well. It's the amount of current passing through an area. It's a flux. Or this is a ds using the notation that we've used here. What that means is that I could write this on the right hand side as that. On the left hand side I have this. On the right hand side I have this. Now what I'm going to do is to pull this over to the right hand side and pull the integrands together. Now, this is true for two different situations. One situation would be if your surface has an area of 0, and another would be if this right here is 0 as well, in general. So let's look at the specific situation where you have del cross B is equal to mu naught times J. And this right here is another example or another expression of Ampere's law. We'll be talking more about this version of Ampere's law later on. This becomes part of something called one of the Maxwell equations. It's an incredibly important equations or series of equations that allow us to talk about light. So both of these are expressions of Ampere's law. We have what we call an integral version and a derivative version or a differential version. So let's talk about the specific case of loops of wires stacked on top of each other. Now, I'm not going to explore this situation when you have a very short series of loops that are stacked. What I'm more interested in is a very long one, and I'd like to know what the magnetic field looks like dead center in between. Now, to help us get there, what I'd like to do is to look at one of the results that we got last time, uh, dealing specifically with coils of wire and magnetic fields. And that's that if you have a loop of wire and you want to know what the magnetic field looks like, a distance of d above it, um, the magnetic field looks a little bit like this. It is mu naught r squared z hat. There's an I there. Over 2 d squared plus r squared raised to the 3/2 power. Now, so imagine being dead center in this very, 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 very long series of loops of wire. So we're dead center here. Let's draw us a little coordinate system. This is something like center right there. And let's just pick this one right here. Let's just pick that one. So the magnetic field that you'd see would look something like let's see, let's do this a little bit better. It's going to look something like that. Now, again, we're disregarding all the neighbors right here. Okay, so with this one right here, the current, which is what these little dots and crosses are representing, is looping around like this. Okay, so we're sort of looking at a cross-sectional cut of a bunch of stacks of wire here. So this one's is going into the board. So you put your thumb in, you curl your fingers around, and what you get is at this very point right here in space, the magnetic field points this way. Okay. Now, if I were to look at its neighbor, the magnetic field at that point would point this way. If I were to look at this one, the magnetic field at this point would point this way. In fact, at the dead center, the magnetic field would point straight up through like this. And it would be constant in magnitude due to how all the neighbors are adding their magnetic fields, all of which that point this way, there. Okay? Now, so what does that magnetic field look like? Well, in a situation like this, if you look at, we'll use this sort of, if you think of this as your loop of current and this being a distance above, in a situation like this, the distance above would be 0. You're at the dead center. Okay? So what's the magnetic field look like at the dead center in a plane in which the current sits? Well, that would be where d is equal to 0. You have an r squared up here. You have an r squared here. R squared raised to the 3/2 power is r cubed. In magnitude. In direction, if you called straight up z, well, that's probably not really good. We'll call it z though. We'll just go with it. So the point that I'm trying to make is that inside here, your magnetic field is pointing straight up like this. Now, so let's clean this up a little bit. There. Wow, that's interesting. I deleted a bunch of my little things. So let's not clean that up. Let's clean it up this way. Now what I want to do is to use Ampere's law to find out exactly what the magnetic field is going to look like on the inside, based off of how much current is passing through my imaginary little thing that I'm going to draw. And my imaginary thing I'm going to draw is going to be a little square or rectangle. We'll go with a rectangle. That is going to have sides of length L and widths of W. Now, so if you look at how much current sits within my little fake circle, and I'm going to integrate this way. This is the direction that I want to integrate along my closed loop, like this. Each wire, each coil that I have, they're connected to each other. Each coil I have here is going to have the same amount of current passing through it, which I'll say is current I. So if I were to count the number of coils here, perhaps there are n of them. So the total current that's passing through here would be 1I for each loop. Okay? So when I write down my Ampere's law, which is going to look like this. On the right-hand side, I'll have mu naught times N times I. Now, so what about the left-hand side? Well, the first thing I'd like to point out is that if you look at the bits of magnetic field that lie in these directions right here, for every one of these that you have that curls up like this, you're going to have a neighbor around over here which is going to curl down like this. And what this does is to cancel out these up and down contributions right here. Okay? So if you wanted to think about it this way, if you have a part that looks like this and a part that looks like this, you have side pieces like this that remain, but the down part and the up part cancel. And since there's a dot product in here, and this would be the direction, for example, on this side that we would be integrating, this would be the direction of any bit of magnetic field that lived here. And what that does is, because the dot product is at 90 degrees, it gives you 0. Okay? So the side pieces right here end up, when you integrate over this and you take into account the direction of the magnetic field and the direction of the path that you're integrating, give you 0. Likewise on the outside. On the outside, we're not asking the question, what's the magnetic field look like out here? So we can sort of a priori get rid of it. We can throw it away. Okay? And we're only interested about the piece that's on the inside, because we want to find out what the magnetic field looks like within there. So here, B is constant. B is in the same direction as L. Which means when you do the dot product, you get V times L. And on the right-hand side, you have mu naught N times I. Now, typically what's done here is you divide both sides by L. You group the L under the N. And this right here is called the number of turns per unit length. Or lowercase n. Okay, so the magnetic field due to a coil or a solenoid that's long looks like mu naught times lowercase n times I at the very center. And that's a pretty big deal. Why is that a big deal? Well, okay, look. Magnetic fields themselves have this curling tendency, this tendency to bend. And any sort of bending to a vector field makes it mathematically difficult to deal with. That's the reason why one version of Ampere's law centers around the idea that the magnetic field curls. It has rotation to it. That's what you see when you see this, okay? Now, if you can think of situations where you can get rid of the curl, then what that does is that makes your math way, way, way easier to deal with. If you could also make your magnetic field uniform, constant in magnitude, then now you have something that you can very easily do math with. And that's exactly what you have sitting in the center of this coil, or in the center of the solenoid. You have a magnetic field that only depends upon how much current is going through and the number of turns or the number of coils that you have inside your solenoid per unit length. So this is an incredibly, incredibly powerful thing for us to use. It's sort of somewhat analogous of in electricity having two flat sheets of metal with opposite charges on them, a capacitor. In between, you have an electric field that only depends upon the charge density in epsilon naught, right? Here you have a magnetic field that only depends upon the current and how many turns of wire that you have, basically per unit length. So you're able to create a uniform constant magnetic field on the inside that points in one direction, and as a consequence, it simplifies the math in a lot of situations quite a bit. Now, solenoids or coils are also used in circuits, which we'll be seeing later on, because they allow you to store energy within the magnetic field, just like capacitors allow you to store energy within the electric field. Their property is a little different. When we talk about it, you'll see how it contributes. In many ways, capacitance and the behavior of coils, or what we actually call inductors, create something that acts a lot like resistance. You'll see why that is here in a bit. That said, we were able to get the relationship for this, the magnetic field at the center, using Ampere's law in a very simple way. And that's the power of Ampere's law. It allows you, if you can find symmetry, to exploit it by drawing your shape, much like you can use with Gauss's law. But again, the caveat is that we're not talking about a conservative field. Now, on that note, I want to talk about Gauss's law and the magnetic field. So one property that magnetic fields have is that they always close back onto themselves to form a closed loop. Here, for example, in the center, you may have this magnetic field that points, but if I were to chop this coil like this, what you would see is the magnetic field would loop back on the outside and go back inside like that, just like a bar magnet. Likewise, if you look at a line of current here, you have this looping around. The magnetic field always connects back to itself. Okay? So as a consequence, let's pretend that you had some sort of surface. I'll draw a square, perhaps. So we have a square like this. And we want to talk about how much current is on the inside using Gauss's law. So imagine a magnetic field going through this Gaussian surface. Maybe, and I'll tell you what, to allow us to see this a little bit easier, let me sort of complete this right here. It's not a very good closed surface, but we'll run with it like that. So here is your field, we'll say, going in. Like this. penetrates this side right here, passes through, and maybe it comes out over here, right? Looping back onto itself. Now the direction of the surface normals are out like this. Coming out here and going in on the back. So if you were to look, for example, at this part right here, you have a magnetic field going in, but you have the surface normal coming out. Here, you have magnetic field out, and you have the surface normal going out. Now, if you pick the shape of this to fit the symmetry of what you're looking at here, the amount of magnetic field that goes through this area over here is going to be equal to the same amount of the magnetic field that leaves. But there's going to be a difference in sign because entering is negative and exiting is a positive. So when you add up the total flux here, when you add up the total amount of magnetic field that goes through these areas, you get 0. So for example, if you were to use Gauss's law and look at a closed surface here and say, okay, what is B dot n hat dA or ds? You would get 0. Now, that said, much like Stokes' theorem has this generalization right here. Gauss's law, I'd mentioned previously, has similar sort of generalization that looks like the integral over a closed surface of A dot n hat ds is equal to the divergence, or the gradient operator dotted A over a volume. Okay, so this right here is a statement of Gauss's law in a similar manner that this is a statement of Stokes' theorem. And so what that says is if I were to take this, I could rewrite this as del dot B d volume equals 0, since those are equivalent to each other. Now again, the only time this would be equal to 0 would be if your volume is 0 or this right here is 0. And having this right here being equal to 0 is more general. So what that says is del dot B is equal to 0. Now look, if I were to put together all the stuff that we have from our discussion about electricity so far, this is charge density over epsilon naught. You have this, and then you have the statement of Ampere's law that I had written down, which looks like this. So the divergence of a field and the curl of a field are enough information to uniquely define all of its properties. So this right here defines most of the properties of the magnetic field. This equation, Ampere's law, is actually incomplete. We're going to talk about how to complete it when we talk about light, which is going to be the last thing that we talk about this semester. We still need to complete the electric field, which is one of the things that we're going to be doing in consecutive chapters, or the ones that we talk about after this. But these are almost at what are called the Maxwell equations. The Maxwell equations basically tell you everything that you need to know about electricity and magnetism. Now, that said, what I would like to do is to take and use Ampere's law again for a problem that is a lot like some of the ones that we've worked previously, and that's a thick wire that has current running through it. I'd like to look at the magnetic field on the inside and also the magnetic field on the outside. So here's a thick wire. Let me create some ends here for our wire. There's a method to my madness. And now we have some ends for our wire. So maybe it's like this. This looks sort of like the cross-sectional area of it, like that. Sort of like that. So were I to pick, some place over here, let's say right here. Whoops, I don't want to do that. What I wanted to do was this. Here's sort of the cross-sectional area of our wire in the middle. Let's say our wire has a radius of capital R. Almost done. Okay, and it has constant I. And maybe I is to the right like this. So what we have here, if we want to talk about what the magnetic field looks like on the inside and also what it looks like on the outside, is a way to relate the current that flows through this wire to its area through the current density. So just to remind you, current density J is equal to the amount of current that passes through an area. And this is a constant current, so I is constant. And what that means is that with a constant area, J is constant, which means that it would be I over pi times R squared, because it's a circle. Okay, that's the cross-sectional area. The current flows through something like this. Okay, so as a vector, J vector would look something like I over pi R squared y hat. Okay, that's your current density. Now, we're going to need that for talking about the inside, because we're going to talk about the outside first. So if I were to look at this thing, staring straight down the end of of this wire. So here's my wire of radius R. The current is coming out towards us, so this would be the direction, we'll say, of J, and also as a consequence, that's also the direction of I. Here is a coordinate system for us, like this. If I relate this to the coordinates that I see here, we would have Z going up, and this would be in the direction of X this way. Okay. So if I want to find the magnetic field on the outside, and I know that there's a total amount of current I flowing through this thing towards me, what I'm going to do is to draw a closed loop around my wire like this. That's no good. That's not a very good closed loop, was it? There we go. There's my closed loop. Now my closed loop is going to have a radius of R, lowercase r. And if I put my fingers in the direction of I and curl them around, what I get is a magnetic field that is going to go around like this. Now what's the shape going to be? Well, look, my wire is circular in cross-sectional area. There's a uniform amount of current that goes through it, which means that as long as I'm the same distance away as to go around from the center, then the magnetic field along this should be the same. Okay, so Stokes' theorem or Ampere's law says here, if I integrate the magnetic field B dot dl, I'm going to get mu naught times the amount of current that's trapped on the inside. Well, conveniently enough, the amount of current that's trapped on the inside of my loop right here is I. It's the total amount of current that we have. We don't know what B is, but if I look here and I think about this as being the direction of dl, okay, so this is dl right here. dl in magnitude is going to equal to R times d theta. Okay, it's along this circumference right here. Now B and dl are going to be perpendicular, are going to be parallel to each other rather, which means when I do this dot product, I'm going to get 1. Likewise, B is going to be constant along this, which means that when I do this, I can pull B out, and really what I'm doing is integrating my dl over the closed loop. Okay? Well, R is constant in dl. Theta is the only thing that changes, and it's going to go from 0 to 2 pi. On the right-hand side, I have mu naught times I. This is 2 pi when you do the integral, which means B is equal to mu naught I over 2 pi R. Which, if you were to go up in here and look at this, mu naught I over 2 pi R. Much like the electric field that sits above a cylinder of charge, looks exactly like the electric field due to a line charge. Here, the magnetic field due to a thick wire on the outside looks like the magnetic field due to an infinitely thin wire. So what about on the inside? What does the magnetic field look like on the inside? Well, that's where the current density is going to come into play. So let me steal some of this and bring this over here just to make my life easy. We're going to copy this and paste right there. And I'm also going to get this right here. And paste it here. So that's gone. Okay, so everything here looks good. Okay, good. All right, so let's talk about the inside. So the trick here is that our current is uniformly distributed across this area right here. So if I were to sort of blow that wire up as a cross section like this, all right, and then let me draw some coordinates on the inside. And then draw my surface on the inside. Maybe like this. And let's not forget, the radius of our wire is capital R. Our little surface that we drew is going to have a radius of lowercase r, just like before. So this is what I want to integrate. Now look, remember, Stokes' theorem, or Ampere's law, only tells you about the field that's due to what's on the inside, much like Gauss's law. And on the inside, we don't have all of the current. We have part of the current. We have the part of the current density that's going through the area right here. Okay? So if I wanted to know how much current that would be, the area of my little surface right here that I drew, that area is going to be pi times little r squared. So here, the amount of current that I have is J times A. Because remember, J is equal to current over area. J is I over pi times R squared, and A is pi times little r squared. The pi's cancel, and this is little r over big R squared. So when I write down Ampere's law and I look at my closed loop integration right here, on the right hand side I have mu naught times I, and in this case I is equal to little r over big R squared. On the left hand side I have B dot dl. Now again, dl is going to be like this, and looking at this is the direction of out, just like this. B is going to be this way, in the same direction, and it should be constant in magnitude along this loop. So what that means is I can pull it out, the dot product is 1, and again I'm integrating over the circumference, which is r times 2 pi. Now, B is equal to mu naught I little r over big R squared divided by 2 pi times big R. So, mu naught I little r squared over 2 pi big R cubed. That's what my magnetic field looks like. And if you take a look at this and you compare this to the magnetic field that you have here, they look basically the same, except you're scaling I based off of what percentage of the current that you have inside your little closed loop that you drill. So as you can see, these things are incredibly powerful. So this is a very useful thing to have. But again, just like Gauss's law, you may be better off actually just doing the full-blown vector integration to try to find the magnetic field, in case the symmetry of the shape in your path that you've drawn doesn't meet the symmetry of the magnetic field. Okay, so that's it for video 2. In video 3, we're going to finish up our discussion about the origin of the magnetic field with the discussion about the interior of materials and how the interior of metals and other materials can act a lot like the dielectric does when it comes to magnetism. And I'll see you then.